Why does the sun actually shine? A weird question since everyone knows it's nuclear fusion. But the sun is actually kind of cold. It's 15 million Kelvin, but fusion reactors on Earth are over 100 million Kelvin. So how does it do it? It's really nothing more than a probability trick. The answer lies in quantum tunneling, and that's where we'll begin. Look at this ball near a hill. If it doesn't have enough energy, it won't be able to get over. If it does, then it will. But in contrast, if it was a quantum ball, the ball could tunnel right through. This is a phenomenon which really goes against intuition, but it will be more rigorously explored now. But first, we need to define some constants. Say we had a potential barrier. Its width would be a, the distance that the particle must tunnel. Its height would be v, the potential energy required, and the energy of the particle itself would be E. You may have heard of the Schrödinger equation, and this is where it comes in. It governs the wave function of a quantum mechanical system, and the wave function squared gives probability density. Determined by Schrödinger, the wave function diminishes exponentially while in a potential barrier, and so does the probability as width increases. We can derive this probability from the Schrödinger equation, and we call it transmission probability. And this equation is useful to show, as you can see relationships between width, height, and mass, and original energy, and their resulting probability changes. Although I will note that this is only for rectangular constant potential wells, and is more generally this, for example for curved potential wells, such as the one that we shall discuss. Now, for quantum tunneling to happen in an identifiable way, we need a finite height, and also a sufficient number of particles, because the probability is very low. Okay, so the sun uses nuclear fusion, and for nuclear fusion to happen, we need to get nucleons close enough together for something called a strong force to take over from the electrostatic force, which acts between charged protons. The strong force is a fundamental force that holds nucleons together. It's incredibly strong, orders of magnitude stronger than the electrostatic force, but acts at very tiny distances, like Velcro. The energy required to overcome the electrostatic repulsion between like particles is called the Coulomb barrier, and it looks like this. The potential energy required gets higher and higher as you approach the proton, due to repulsion, and then suddenly goes negative when the strong force takes over. This is where all the quantum tunneling comes in. See, protons are quantum particles. They are waves of probability, and therefore have a non-zero probability on the other side of the potential barrier, so they can tunnel. Now, we can find a rough probability of this happening, and the answer is a tiny 1 in 10 to the 28. But remember the point about having a lot of particles. There are over 10 to the 56 particles in the core of the Sun, so with a tunneling probability of 1 in 10 to the 28, the number of particles tunneling is sufficient enough for fusion to happen effectively. And we can't do fusion like this on Earth because we simply don't have that many particles. The same principle actually underlies alpha decay, but in the opposite direction.